Now that we've been introduced to the concept of verifying trigonometric identities, I'd like to actually try this process out a couple times. So let's take a look at a couple of examples. So for our first example, we have the sine of theta plus the cosine of theta quantity squared plus the sine of theta minus the cosine of theta quantity squared is equal to 2. Now in a previous video I recommended that you start with the more complicated side. So what do you think? The sum of two squares that both need to be FOILed out, or 2? I'm thinking left-hand side. Now, as we perform each of these manipulations, I will be listing a justification for each of the manipulations that we do. So, I am going to go line by line with each step, and then over on the right-hand side in purple, I'm going to give a justification. Now, if it's a step of algebra, I'm simply going to justify it by saying algebra rather than specifying exactly what kind of algebra. If I have to use a fundamental identity, I will definitely do so. Now, with that in mind, first thing I'd like to do is FOIL the first set of parentheses. So foiling inside the first set of parentheses will give us sine squared theta plus 2 sine theta cosine theta plus cosine squared of theta. Doing the same thing for the second set of parentheses is going to give us sine squared of theta minus 2 sine theta cosine of theta plus cosine squared of theta. The justification that I'll give to this step, this was a step of FOIL, which technically would just be a step of algebra, so we'll identify it as that. Next, I'm going to combine any like terms that I see, which is another step of algebra. I see that we have a sine squared of theta plus a sine squared of theta. That'll be 2 sine squared of theta. We have plus 2 sine theta cosine theta. We have minus 2 sine theta cosine theta. Those will cancel each other out. And we have cosine squared theta plus cosine squared theta. That would be 2 cosine squared theta. Now that was combining like terms, or we can simply refer to that as a step of algebra. Notice at this point we have a common factor that we can factor out. Now, eyes on the prize, I'm taking a look at the final answer. Final answer is supposed to be 2, and I notice that both of these terms have a 2, which is why I decided to factor it out. Justification for that step was a step of algebra. And finally, the sine squared of theta plus the cosine squared of theta, we finally get to use a trigonometric identity. That is 2 times 1. That is a Pythagorean identity. Now, I really don't feel the need to justify that 2 times 1 is equal to 2, so I'm just going to call that 2 and call it good. So, a lot of algebra, not a whole lot of trigonometry in this example. Let's see if we can try out another one. Directions are the same as before. Verify the identity, justify each step. I'm going to start with the more complicated side. Now, in terms of their algebraic properties, these sides look to be about equivalent to each other. But I would consider the left side to be more complicated, as I tend to work less with the cosecant than I do with the sine. So I'm going to start with the left side once again. So we'll call this cosecant of v minus 1 over the cosecant of v plus 1. And then to the right of that, I will start including justifications of each step. Now, one of the basic strategies that we introduced is, when dealing with things like the cosecant, the secant, the tangent, the cotangent, expressing those in terms of their sine and cosine using fundamental identities might be advantageous to us. So using a reciprocal identity, I can turn the cosecant of v into 1 over the sine of v. Now, it doesn't get flipped across the big fraction bar due to the fact that there is still a plus 1 and a minus 1 to deal with here. The justification for this step will say reciprocal identities. Now at this point I notice that we have fractions inside of a fraction. Yo dog, I heard you like fractions. So what I'm going to do is clear out the smaller fractions that are inside of the bigger fraction by multiplying top and bottom by the sine of v over 1. This is actually referred to as a complex rational expression, and this is one of two different methods for how to get rid of the fractions inside of the fractions. I'm going to distribute the sine of v over 1 to both terms in the numerator as well as both terms in the denominator. So first term in the numerator, 1 over the sine of v times sine of v over 1. Those will cancel to become 1. Sine of v over 1 times 1 will simply be the sine of v. In the denominator, sine of v over 1 times 1 over sine of v, same algebra as what we saw on the top. And sine of v over 1 times 1 will be sine of v. That was making use of the distributive property, as well as some reducing, but really that was simply a step of algebra. You'll notice that the expression that we come up with is the same as the expression that we had on the right-hand side of the identity. Therefore, this problem is done.